EC 201, lecture 12. So for a quick recap of what happened last week, we are at this point where we now understand how this amplifier circuit came about. We know how to find its gain. We know how to find the swing limits of the. Alright, this is what we know. So the next thing is to figure out if this solves all our life problems, then we move on, we are done, right? And the course is over. Unfortunately, as you probably know, if this solved all our problems, then this course won't be there. And so obviously the truth is that there are some problems with this circuit. We'll figure out what the problems are, and then we'll try and go and fix the problem. So you come up with another circuit. Hopefully the problems in that circuit will be, you'll have gotten rid of some of the issues that are there with this circuit. And nothing in the world comes for free. So you go and try something. You solve one problem, you introduce the next, and so on until we find enough material to finish to fill up 50 lectures so that the semester is over. Okay. So what do you think are the problems with this circuit? As engineers, what all do you think can happen? And which is the root of all troubles? Which are the problem candidates? Okay, we don't have infinite capacitors. Okay, nonlinearity. The argument is yes and no. Yes, because nonlinearity causes bad things to happen to the output sine wave. However, we've already gone and figured out ways in which you restrict the swing to make sure that the output kind of still looks like there's some semblance to the input. Okay, so that this is where all the swing limit stuff comes about. So let's imagine that you guys are designing this and then planning to sell it in the mass market, right? So millions and millions of these will be sold. What problems do you think you'll encounter if you just mass produce these things? Let's assume for the time being that these infinite capacitors are somehow possible. What else do you think are the problems? One, somebody says tolerances. So which means what? What do you understand by the word tolerance? Do you guys do engineering drawing these days? When you see these right? These machine drawing, I think it was called, where you have some weird looking picture and then you got to on every dimension there will be some plus minus something, right? Hopefully the plus minus, the quantity that comes after the plus minus is smaller than the original quantity itself. So what does this plus minus mean? There is so everything you do, there is a tolerance to it, and if the tolerances are loose, it basically means that you have a cheap manufacturing process. Alright, and of course you can beat your head and make the dimensions very very tight, kind of a little obvious that it pushes up manufacturing costs. So what is true of the mechanical folks is also true of us. If you want to make an integrated circuit where all the transistor and the resistors are all on the same chip, it turns out that when you try and make these transistors, you say, for example, the transistor parameters. What are the transistor parameters as far as you are concerned? What determines the transistor? The mu n C of W by L and Vt. It turns out, so these are, that W by L is simply, as I pointed out, is a geometry related thing. Vt is the threshold voltage, and those of you who have done devices know that it's some weird complicated formula, right? Cox and all sorts of stuff. Okay. Similarly, mu n is the mobility of electrons in the channel and Cox is the gate to channel capacitance. And it turns out that these quantities vary, first of all, with time. When I say vary with time, it means that over time, for example, the temperature varies and maybe there is some mechanical stress on the IC. All these quantities, mu n, Cox, Vt, for example, are all variable. First of all, even if you made a transistor and measured mu n, Cox and Vt at this point in time, these numbers will fluctuate with, so what you measure after say 3 months at maybe a different room temperature is not the same as what you measured today. This is a fact of life. Okay, you can't do anything about it. The next thing is that if you made millions of transistors on the same chip, while it is true that the properties of the two devices made side by side are roughly the same, okay, you cannot guarantee that the threshold of one transistor will be exactly the same as the threshold of the neighboring transistor. Problem which is a lot less on IC than in discrete circuit. So if you go to the Ritchie Street and buy two transistors which are nominally the same make, alright, have the same part number and so on, and if you measure the threshold, you will find that the threshold will be off by maybe 100 millivolts, 50 millivolts and so on, and the manufacturer will quite honestly tell you that look, the nominal threshold voltage of this device is 0.8 volts, but the threshold will lie in plus minus 100 millivolt range from around the nominal. So which means that if you buy a transistor off the shelf, then the threshold voltage can be anywhere between 0.7 volts and 0.9. So such variations are called random variations. So for example, Vt varies across different devices, and so does mu and C off, but not so much. The next thing is, our circuit has got transistor, it's got resistor, okay. So we look at the variations in the transistor, and we have now reconciled to the fact that the biggest culprit in the whole story seems to be this variation of Vt. Mu and C off is also a culprit, but not quite to the same extent as the variation in Vt. Alright? And why are we so hung up on Vt? First of all, do we care that Vt changes? Why? Is there a more fundamental problem? He says Vt changes means Vd sat of the device, that is VGS minus Vt will change. Correct? Reading between the lines from what he said, it means that the swing limits will change and so on. But is there a more fundamental problem? Fundamentally, the current itself in the transistor will change. So let's say we had biased this in our example we discussed in the last class. The gate source voltage was I think about 0.7 volts. 0.7 volts is the threshold of 0.5 volts. So we thought the threshold was 0.5 volts, and then we went and calculated RA and RB such that the gate potential is 0.7 volts. Now if the manufacturer says, oh, the threshold is uncertain by about 100 millivolts, you're now stuck with a VGS minus VT of 100 millivolts. If the threshold kind of moves to 0.6 volts rather than 0.5 volts, your bias voltage is still 0.7 volts, which means that the VGS minus VT has gone down by a factor of 2, which means that the current has gone down by a factor of 4. The MOS transistor is square lawing VGS minus VT. If the current has gone down by a factor of 4, what can you expect for the transconductance of the device? Gm is proportional to VGS minus VT. So if VGS minus VT has gone down by a factor of 2, the Gm has also gone down by a factor of 2, which means that the swing limits are completely screwed up now. And more importantly, the gain of the amplifier, which was what, 10 or something last time, has now dropped to 5, because the Gm has gone down by a factor of 2. So the bottom line in all this is that variations in the device parameter can lead to a change in the gain of the amplifier from the intended value. In discrete circuits, it turns out that this is a problem. What is the difference between a discrete circuit environment and an integrated circuit environment? It turns out that on an integrated circuit, you make a transistor, you think the threshold will be 0.6 volts, but the threshold turns out to be 0.5 volts because of some manufacturing variation. However, if you made another transistor on the same integrated circuit, then the other transistor will also nominally have the same threshold. This is exactly like copy and paste in a word processor, right? So you type some screwed up text and you copy and paste it You have another copy of the text, but it is just as screwed up as the original. Okay. So this is multiple copies of the same device have the same properties. You are hoping to get an elephant, but you got a donkey instead. But on an IC, it means that if you try this whole process again, you can be sure that you will get another donkey. Is this better, or are you better off or worse off? At least you know that you are getting a donkey, right? So the fact that you can make multiple copies of the same thing is actually very profound, and it's a fundamentally important thing to have. Simply because you can make measurements, for example, on the copy, figure out what all is wrong with the copy, and then whatever you need to do to correct that copy, if you apply the same correction to a neighbor, then the correction which works for him also works for the other chap. Does it make sense? I mean, this is a property which is used in medical science all the time. So when you go to medical school, what happens? You learn about everything about the human body, right? And the only reason it makes sense is that human beings everywhere have pretty much the same basic constitution. So what works for X and Y also works for Z. So when you go to the hospital and have fever, he gives you crocin, and he gives the other fellow also crocin. And the reason why this works is that all of us are nominally identical, right? There are only random variations. I mean, simply statistically, there are just random variations from person to person. Does it make sense? On an IC, the random variation is much smaller, which means that whatever happens to one device, if you did the same bad things to the other device, it would also respond in exactly the same identical manner. Okay, so this is true of transistors, this is true of resistors. Anything you make on a chip, you can expect two identical copies to be extremely similar. Another medical analogy is the case of Siamese twins. You understand? So they have gone through the same process right from beginning to end. So you can expect that the two twins will be identical in a whole bunch of respects. Okay, I mean, visually obviously they look very similar unless you have a very trained eye, and the differences are all random differences. The same thing that happens in an IC. You put the wafer through the same furnace. So if you make two transistors next to each other, they will go through the same process. So they will get heated to the same thing. They will get doped to the same extent. All right, and when they come out, they have the same property. All right. So the same thing happens even with respect to resistors, or capacitors for that matter. So on an IC, for example, even though RA here and RB here may be, say, grossly off from their nominal values. You wanted 10K but you got 15K. However, if you took the ratio of two identical components, what would you expect? So you are making two resistors. One resistor was 10K, one resistor was say 20K. Alright. However, because of some big screw up in the fab, instead of 10K, you got say 15K, which means that instead of 20K, you will get 30K. So even though the absolute values of resistors are different, you can bank on the ratios of like components to be very tight. Does this make sense? So in other words, in this circuit, if you make the circuit on an IC, even though RA and RB vary by a whole lot, the gate potential only depends on VDD and the ratio of RA and RB. And we know that ratios of like components on an integrated circuit are controlled to a very tight tolerance, simply because both are identical, both components undergo identical process steps, which means that even though there is a screw up in the process of making the transistors or the resistors for that matter, since both of them undergo the same steps, Okay, whatever happens to one happens to the other two. So the ratio of the two simply is very, very accurate. So on an IC, multiple copies of the same device have the same property. In other words, ratios are extremely well controlled. So in other words, the nominal VT of the that you wanted to make was say 0.7 volts. If you made two identical transistors in the same integrated circuit, then you could end up with both of them being 0.8 volts or both of them being 0.6 volts. Okay, but the key point is that both of them are the same and both of them differ from the nominal value. So now that we understand what the problems are, let's revisit this circuit and see what can happen to this chap. So as we already discussed, what are all the problems with this circuit? One is that the DC current, so the bias current in the transistor, which is M1, varies with the threshold VT. The bias current varies with as VT of the device changes, which means that swings and incremental gain are now dependent on VT. You understand? Why is the incremental gain dependent on VT? Please note that the gate source voltage of the MOSFET is fixed. It is VDD times RA, RB by RB plus RA. Okay? And that guy doesn't know that the transistor threshold is changing. That's a fixed voltage. Okay? And if you want to make it a little clear, you can think of this as far as the biasing is concerned. Let me just worry about the biasing now. So I will get rid of the incremental part. And as far as the biasing is concerned, the whole bias arrangement on the gate side is equivalent to the following, which is what we knew in the first place, which is VDD times what? RB by RA plus RB. Okay, and this is RA parallel. Had actually called this VGS1, and we said why bother with another battery, we can derive it from VDD. Okay, so this is in fact an earlier step than what we finally had. The incremental gain depends on VT simply because the gate source of the MOSFET is a fixed voltage, and that is equal to VDD times RB by RA plus RB. So as the threshold voltage of the MOSFET changes, the VGS minus VT of the MOSFET goes on changing, which means that since the bias current of the MOSFET is proportional to VGS minus VT the whole square, the drain current of the MOSFET keeps changing, which means that the GM also keeps changing, which means that the swing also changes. Is that understood? So the root cause of all these problems is now what? The problem is this: bias current in M1 varies with VT. And why does it vary with VT? Because VGS is, the true culprit is that when the VT of the device changes, the VGS still remains fixed, and the device reacts to not VGS but to VGS minus VT. Okay, and that's the reason why everything else, once the bias current changes, the small signal incremental equivalent circuit of the MOSFET changes, which means that everything is up for a toss. So, as smart engineers, what will you do? What could you do to fix this problem? If somehow the bias generator or the battery here, for example, if this guy, if we knew the threshold, then I would make this battery, I want a VGS minus VT of 200 millivolts. If the battery somehow knew about the threshold voltage, then what could we do? If we knew, for example, that we wanted VGS minus VT of 200 millivolts, Then if we somehow knew Vt, then we could add, instead of VGS1 being an absolutely fixed potential, if it was Vt plus 200 millivolts, then when Vt changes, we don't have to worry about it because the battery will also change adaptively, so as to make sure that VGS minus Vt of the MOSFET is still the same. Okay, does it make sense? In other words, instead of having a fixed VGS, if we somehow found the exact value of VGS required so that the transistor has the current we want. Okay, for example, what was the current we had last time? So in our example, ID was 100 microamperes. So let's say we want to make sure that the bias current in the transistor is 100 microamperes no matter what Vt is. See, our aim is now to make sure that instead of applying a fixed voltage between the gate and the source, apply a voltage such that the current through the drain is always the desired current, which is 100 microamperes in our case, regardless of the Vt of the device. In other words, if we somehow answered the question, what gate source voltage must I apply so that the drain current is 100 microamperes, and use the answer to that question as the battery, then the current in the drain will be 100 microamperes. You understand? So far you have been doing the forward thing, which is you apply a VGS and take whatever ID you get. Okay, I mean, it's not as dumb as that, but you have used the formula. Okay, you have used VGS is whatever, right? Some 0.7 volts, Vt is 0.5 and all this, and found ID. What we need to really be doing is to be asking this question and answering it, which is, if I want 100 microamperes of current to flow through the drain of the transistor, what gate source voltage must I apply? So how will you find the answer to this question? Pardon? Okay, let me revert this. So you went to the lab. I gave you a MOSFET. Okay? I told you, well, I don't know the threshold of this MOSFET. I know it's around 0.4 or 0.5 volts, but I don't know the right value. In other words, you have this transistor. The threshold is not known. Neither is mu and C off. And I insist that you tell me what voltage I must use between the gate and the source so that the drain current of the transistor is some desired value, say 100 microamperes, when the transistor is in saturation. You understand the problem? So you get into the lab, I give you a MOSFET whose mu and C off and Vt are unknown. Alright? And I give you the job of figuring out what gate source voltage must I apply so that the drain current in the MOSFET is 100 microamperes when the transistor is operating in saturation. I find the answer, then I just go run out and buy a battery of precisely that value and pop it in, and lo and behold, the drain current must be 100 microamperes if your answer is right with this problem. What would you do? So it's a valid way of doing it. She says you put in two values of VGS, you find ID, you measure ID, then you can go work the math, right? You find Vt and you will find mu and C off. You need two variables, I mean you need two equations. You got mu and C off and you got Vt to find. Okay? You put in two different values of VGS1, measure the drain current, figure out Vt and mu and C off, and boom, you can get the VGS1 required so that the drain current is 100 microamperes. Alright. So can now somebody come up with a smarter way of doing it without having to do any math at all? What all are the conditions that have been put? So first of all, to figure out, you all agree from these two guys that we need certainly a variable voltage source. So what both these gentlemen said is related, and this is what I would do. I need to keep M1 in saturation, correct? So what potential should I connect the drain to? I mean, I can't obviously leave the drain floating. So to keep the transistor in saturation, what would I have to do? Yeah, but I don't know what VGS I need. So what would I do? What's the best bet? Choose a large VD, and I mean, of course, not so large so that it will blow the transistor, but a sufficiently large VD. So let me call that VDD. And I need to measure the drain current. Alright, so which means what? I will put an ammeter. Right, so this is an ammeter. So what is my approach? So apply VGS, measure ID. So if ID is greater than 100 microampere, what does it mean? If ID happen to be greater than 100 microampere, does this mean that you applied too much of voltage or too little of a voltage? It basically means that VGS is greater than VGS1, which means that what must you do? Reduce VGS. On the other hand, if ID is less than 100 microampere, what does it mean? VGS is less than VGS1. So what must I do? Must increase VGS. Does that make sense? So what I need is a variable voltage source and an ammeter. Okay? So I look at the ammeter reading. If it's smaller than 100 microampere, I simply crank up the voltage source. If it's greater than 100 microampere, I reduce the voltage. Now, this is a logical common sense thing that any one of us would do. Of course, if one wanted to do the math and do it, you could also do it. But can somebody point out a disadvantage of doing what the first person said, which is apply VGS1, apply VGS2, find mu1 CoX and find VT? I mean, no, I'll grant him the fact that we made VDD sufficiently large so that it is in saturation. Can somebody think of a disadvantage of that method? In the second method where we measured the current to the MOSFET and varied the gate source voltage, did we need to make any assumption on the nature of the device? If it was being square, if it was cube, what would happen? In the first case versus the second. The way of doing it with two VGSs and then finding the characteristics assumes that you already know the characters. On the other hand, the second method where we just monitor the output current, okay, and just go on tweaking it, made absolutely no assumptions on the nature of the I versus VGS dependence. And it turns out that I have fooled you into thinking that the MOSFET is a square law device. In reality, it's neither square law, okay, nor of the right form that I have discussed in class. This is just convenient for hand analysis. So the real function is actually a very, very complicated function. All right. So if you assume that it was square law and then did all the math, you are likely to end up with some error. All right. Whereas if you use the second method, which is you measure the current in the drain and go on tweaking VGS1 until the drain current equals what you want, then in the whole process of finding VGS1, we have not made any assumptions on the nature of the nonlinearity at all. You understand? So, so this is what is called what? What have we done? Can you verbalize? What is this called? This is called negative feedback. Why is it called feedback? And to give you a very simple analogy, right? If somebody asks you for directions, you are here. Somebody asks you for directions to the EE office. There are several ways of doing it. One way which I could think of is the following, which is I will say, okay, you go maybe 4 meters up front, make a right, go forward by 2 meters, then you will get an elevator, You get into the elevator and move up by 10 meters. You get out of the elevator, make a right and walk 100 meters straight. Okay, then make a right and then walk 10 meters, and then you get into the department office. I mean, this is a perfectly valid direction. Okay, this is what you get in Google Maps. You understand? Drive from place A to place B. They will tell you you drive 1.5 miles here, make a right, drive 3 miles there, and if you're not keeping track of how many miles you've driven, you will be completely lost. Another more sane way of giving direction is to say walk up until you find the elevator, take the elevator, hit 1, you go to the first floor, make a right and keep walking until the dead end. You make a right and then walk until you see some kind of dingy corridor, and that's the EO. You understand? So what are the differences between these two? The first way of doing it is what is called an open loop method, because you're giving x, y, z, comma, t versus time. Okay, this is what you're supposed to do. Alright? So obviously if there are errors in the numbers you get, the poor fellow will go up the elevator, make a right, and instead of making a right at the dead end, he'll make a right before and end up in the men's room, which is like a terrible thing to happen. So this is a problem associated with all open loop type affairs. Okay. On the other hand, a closed loop situation is what I've just described earlier, which is instead of telling him to turn right after 10 meters, you say you keep going until you see the dead end. At the dead end, you make a right. Okay. So what is if you gave somebody such directions, what is that person doing continuously when he is on the first floor? He is subconsciously looking at the difference between his position and the position of the dead end, and then when that error between his position and the position of the dead end reaches 0, he takes the next step. You understand? I mean, this way you can't miss the dead end at all. I mean, unless you can't figure out what the dead end is. And that's precisely the same thing you're doing here when you're trying to set the bias current to the MOSFET. You're measuring the current in the drain, you're comparing it with what you want. Alright? You're using the error between what you want and what you have to go and tweak VGS1. So in feedback parlance, this 100 microamperes is called the reference quantity. The actual drain current to the transistor is the output quantity. Alright? And you use the error, which is the difference between the output quantity and the reference quantity, to go and tweak the stimulus to the system to make it give out the reference in the end. Does this make sense? So in other words, you are comparing the drain current of a transistor ID to some reference current IREF, and you use the error between, whenever you compare, what are you doing mathematically? Bill Gates has got so many millions. Your roommate has got whatever. Multiplied by 10 power minus 9. So what do? When you compare, equivalently it is subtraction between the two of them. Right? So comparison even though you're not used to thinking about it in mathematical terms, it is basically subtraction. Correct? So you compare the output ID with the reference and use the difference, which is IREF minus ID, to go and control the animal, which is the transistor, and the knob you use to control the transistor is VGS1. You understand?